we now know, we're talking about generic global rigidity. We now know that every generic globally rigid framework is redundantly rigid and D+1 connected. And we have this stress matrix, which gives an algebraic sufficient condition for global rigidity. And we also talked about one-dimensional global rigidity, where we showed that every two connected graph was globally rigid on the line. And sort of the combinatorial step there was pretty easy, and I think I left it as an exercise. It was to show that every minimally two connected graph could be reduced to a smaller two connected graph by a one reduction, so by the inverse operation to a one extension. So now we really want to do that in 2 dimensions. So we want to characterize global rigidity for frameworks, generic frameworks in R2. And so we're going to be looking at when can we find a degree-free vertex and when can we apply a one reduction to it. But this is going to be much more complicated. And so I won't manage to do it all in this lecture. So it will take at least 2, probably 3 lectures. This particular lecture, I think, is kind of a difficult one to give because it's going to be very technical combinatorics. But actually, so I have 2 papers where I look at analogous results for other sparsity matroids, and still I read the paper of Berg and Jordan that today's lecture is based on and wonder how they came up with it, because it's very intricate and you'll see as we go, but I think it's kind of a hard lecture to present. So I'm specifically saying this because I would like it if you interrupt me. If things become unclear, then please do interrupt and we'll try and go through it because it's going to be quite technical combinatorics. Okay, so remember we have the generic d-dimensional rigidity matroid, RD. So this is just the linear matroid or the row matroid of the rigidity matrix at some generic point P. So a state RD here, but we're only going to be interested in the 2-dimensional rigidity matroid. So, and in particular, we're going to be interested in dependent sets in the rigidity matroid, and a fundamental case of dependent sets is circuits. So we are going to define a graph. So I know in matroids the circuits are edge sets, but we're really going to abuse notation and think of a graph as a circuit. So if we have the rigidity matroid of some graph, then a subgraph of it, H, is called an R2 circuit if the edge set of H is a circuit, i.e. a minimally dependent set. So the edges of H, the rows of the rigidity matrix, are dependent, but if you take any one edge away, those rows become linearly independent. And what we're really going to do is think of circuits in this matroid. We're going to think of them as just purely a graph theory condition because we're going to use the Polychek-Geringer-Lemma theorem. Okay, so as a corollary of the Lemma theorem, you can deduce the following. So a graph is an R2 circuit if and only if it has 2v minus 2 edges. And if you take any one edge away, you're minimally rigid. It doesn't matter which edge you pick, you take any one of them away, you get to a graph of E equals 2v minus 3. And because you had a circuit before, by Mans Theorem, you will end up with well, just because you had a 2v minus 3 circuit before, you take one away, it becomes minimally rigid. And this is equivalent to saying the number of edges is 2v minus 2 still, but we know Mans Theorem, which expresses minimal rigidity as a purely graph theoretic property. So it says the number of edges induced by any subset X with a sufficient number of vertices is at most 2x minus 3. And of course, now we have the additional condition that the size of X has to be strictly less than the whole set V, because we know V has a minus 2 here rather than the minus 3 we have for subgraphs. So Lemans condition would have a 3 and a 3, but we know it's a 2 in total, and it's 3 after you've deleted any edge, say, and it's 3 for any proper subgraph whatsoever. So these are the circuits in this nice matroid. Okay, so
sorry,
I guess I've answered a question.
Yeah, for the first condition up there, up above, we're saying G is an R2 circuit because that's equivalent to the second one where G is minimally rigid. Is that because any subgraph of G would be independent in the rigidity matroid?
Yes, so if I give you a circuit and I take any edge away or take any proper subgraph, then you'll be independent in the rigidity matroid. I mean, in higher dimensions than 2, it's not true that circuits are always rigid. So I'm sort of using Mans Theorem, which I haven't told you I didn't say a proof of this lemma to deduce this, because Mans Theorem implies that all of the circuits have exactly 2v minus 2 edges, and when you throw one away, then the rows are independent, and it's got 2v minus 3 edges, so it's got the rank. It's the full thing for the rigidity matroid.
Yeah. Sorry, it's just sort of understand that out loud, but yeah, thank you.
Great.
Tony, can we just pause and look at these for a moment?
Sure. So do you want me to re-explain, or do you just want to think for a minute?
Tony, when you say G is an R2 circuit, can I think that the G is an R2 circuit on the complete graph with the same number of vertices?
Yes, yes.
Okay, I have a question about the I of x less than or equal to.
Sure.
Wasn't it a greater than or equal to in Lemans theorem?
So Lemans theorem said G is minimally rigid if and only if E equals 2v minus 3 and I of x is at most 2x minus 3 for all x in V, with x greater than or equal to 2. So the sort of motivating example was something like this, where you really don't want it to be bigger than 2v minus 3 for subsets, because then you can have something like a K4 here, which has wasted edges, even though it satisfies the count. So it's definitely a less than or equal to, and it's the same less than or equal to here, that the only real difference is the change from the 3 to the 2 for the full graph.
Okay, great, thanks.
Okay, is everyone happy?
No, I don't understand that that example that you just gave. Why is it rigid? I don't see
This
that.
one's not. So sorry. So this is an example why you needed. So I thought Alex asked about this inequality, and so this is an example that doesn't satisfy what's over here. So it satisfies the equality, but it does not satisfy the inequality for this K4 subgraph. And it, as you I guess you worked out, it's flexible, because this 4 cycle at the side can just move.
Okay, thanks.
So basically, to get a circuit, you take like a 2-3 tight graph and add an edge, but you want to make sure that all subgraphs still have this 2x minus 3 condition.
Yes, so you're exactly right. So if you take any 2-3 tight graph and you add an edge, you will get a circuit. But what I want in my graph to be a circuit is for that circuit you get to be the entire graph. So here's a sort of 2-3 tight graph. If I just add an edge, then what you can see here is that the circuit I've found is this little K4 in the middle here. And you've got bits that just hang around. So for example, if I chose to delete this degree 2 vertex, I would take the total count of 2b minus 2 to 2b dash minus 2, because I just lose 2 from the 2 edges and 1 times 2 vertex. So you're right, that you take a Lemans graph or 2-3 tight graph and you add 1 edge, but for that to be, the entire graph to be a circuit rather than just contain a circuit, you have to be careful of which Lemans graph you pick to start with.
Okay.
Okay, so I will have some examples as we go, so hopefully it will start to become clearer, but please do keep interrupting if anything's unclear. So this lemma is just sort of a motivational thing. So what we're really going to be interested in is D+1 connected redundantly rigid graphs. So we're in 2 dimensions, so 3 connected redundantly rigid graphs. So I just thought it's worth mentioning that redundant rigidity is very intimately linked to circuits. So again, I'm not going to give a proof, but this lemma is hopefully easy. So a graph is redundantly rigid if and only if it is rigid. Clearly redundantly rigid implies rigid, but also, as well as being rigid, it must be that every edge belongs to a circuit. So if it's rigid and every edge belongs to a circuit, if I throw any edge away, I don't change the rank. So it's still rigid, so it's redundantly rigid. And so this is the kind of motivation here. But what we're saying is we understand rigid graphs in 2 dimensions. We want to understand circuits. And then that will help us to understand redundant rigidity. Okay, so here's a fact. I mean, so we just go back up. We know the total number of edges in a circuit is 2v minus 2. So the average degree is slightly less than 4. But we can't have a degree 2 vertex from this sort of discussion we had here. So the minimum degree is always 3. And so this is going to be helpful for us. We have a degree 3 vertex. We now want to find when we can reduce it in by a 1 reduction. As an aside, I've put an exercise in which tells you that this minimum degree, at least as a bound, not as a precise answer, sort of applies in any dimension. So it's not so hard, and you can look, actually you can look it up if you find the right reference if it becomes tricky, but an exercise would be to show that every circuit in the d-dimensional rigidity matroid is d plus 1 edge connected. And if you're d plus 1 edge connected, then the minimum degree is certainly at least d plus 1. So this fact actually generalizes a bit. It's not true that it's equal to d plus 1 all the time, but it's at least d plus 1 all the time. Okay.
Is it clear that it's 3? Why can't it just be bigger than or equal to 3?
Oh, so in a 2-dimensional circuit, we have E equals 2v minus 2, which says that 2e equals 4v minus 4. And so twice the number of edges is equal to the sum of the degrees by the handshaking lemma. So if every vertex had degree 4, then 2e would be equal to 4v, which is bigger than 4v minus 4. So you must have something less than 4.
Makes sense. Okay.
Okay, yes, so remember at the end of the last lecture, what we were doing was we were proving the one extension operation preserves global rigidity. So everything we're going to get from a globally rigid graph by one extensions will be globally rigid. So we talked about small complete graphs then. K4 is a very simple example of a R2 circuit. It's the smallest one. So if we take K4, we showed it was globally rigid last time. Everything we get from K4 by a sequence of 1 extensions, it turns out is actually a circuit as well, and is a globally rigid one. So we're sort of looking at the right kind of thing for our global rigidity problem, but we're just in a particularly special case with circuits. But last time we also showed that we were doing sequences of edge additions and 1 extensions, but edge additions clearly can't preserve the property of being a circuit. You know the total number of edges is this. If you add 1 in, then that fails, and so you go outside the class. So we're going to forget about the edge additions part and just do 1 extensions. So here's a couple of examples of circuits. So first of all, G. So here we have 4 vertices of degree 3. And so what's the point in this example? So what would happen if we did a 1 reduction? So let's say we pick this vertex, so I'll just draw it here. So the rest of the graph would stay the same. We want to reduce this vertex by a 1 reduction. So its neighbors are these 3. 2 of those options are ruled out because we don't want to duplicate an edge. So our only option is to do this third one, and we add this edge. But so what happened when we were doing rigidity in the Pollaczek-Geringer theorem was we picked a degree 3 vertex, and we were able to prove we could always reduce it to a smaller 2-3 tight graph, and that would then made our life easy. So this here showed that the only thing I could do to reduce this vertex here was reduce to this smaller graph, which has a K4, which is the circuit, and a degree 2, which is not possible. So we did find a smaller graph from this reduction, but it wasn't a circuit. It contained a subgraph that was a circuit, but itself it wasn't a circuit. So that 1 reduction was not possible. It's what I will call a non-admissible 1 reduction. Okay, and notice then by the symmetry that if I pick this degree 3 or this one, you get exactly the same graph up to isomorphism. Oh, I think there's a question in the chat. Sorry, I'm not quite so good at following the chat at the moment. Is there an example where every edge belongs to a circuit, but the graph is not rigid? Yes, so there's trivial examples. So suppose you have a complete graph with 100 vertices there and a complete graph with 100 vertices here, but they're not connected. So it's not connected, so it's clearly not rigid. Just fix one component and move the other one. But K4 already is already a circuit. So in fact, if you replace the K100 with just this graph on two K4s, every edge is in a circuit because both K4s are circuits, but it's not rigid. And you could do the same example if you have them share a single vertex. So you have to be a bit more careful than just saying every edge is in a circuit. Okay, so yeah, so going back to this picture, so what we just said is it's a circuit, but every possible degree-free vertex and every possible one reduction at a degree-free vertex gave us a graph which was not a circuit. So this says that this particular circuit here cannot be obtained from a smaller circuit by the one extension operation. The saving grace for us is that this circuit has a, I don't indicate it in red, but let me do it in green here, has a two vertex separating set here. And so what we're going to show is if you're free connected, which we need for redundant rigidity anyway, then our life is made easier and we will be able to find some vertex to reduce and which the resulting graph is a circuit. But even if we assume free connectivity, like in this graph H, it's not true, the nice thing like it was in the Lemma case, that every vertex of degree free can be reduced. So that's my next example. So if we kind of ignore the things around the outside and go back just to this example H. So what happens in H? So H has degree free vertices here, 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 and here. If we take V, imagine you did a one reduction at this vertex V. Because all three of its neighbors have degree free, one of those neighbors will drop its degree to 2 when we do the one reduction. I'll either add this edge or this one. Whichever one I pick, the third vertex will have degree 2. And so just like down here, it won't be a circuit. So V is not reducible. So it's what we will call it non-admissible when I define that shortly. But in H, it is true that there are some vertices that can be reduced. So for example, this one, if I take this vertex on the left and I reduce it and add that edge, then you can check for yourself that will be a smaller circuit. So reducing the blue vertex and adding the dotted edge from V down to this high degree vertex will be okay. And so that's what we're going to have to do. We're going to make a connectivity assumption on our circuits, and then we're going to find that still some are not good, but some are good. And we're going to have to prove that a good one always exists. Okay, so that's what I say here. In the free connected graph H, there was an irreducible vertex, but there are also good ones.
Hey, Tony.
Okay, so
did we already see that 3 connectivity is required?
Required for what?
For global rigidity?
Yes, so remember we showed that if you're globally rigid in RD, then you must be D+1 connected. So in the plane, the example would be if you break it up via 2 vertices. So this is not free connected, but you just put a line through those 2 vertices that separate the graph and reflect one component across the separating set just reflect through that line.
Oh, I remember this. This was last lecture.
Sorry?
Last lecture?
Maybe 2 ago, I think, but very recently, yeah.
Okay, thanks.
Yes, so circuits like this one don't need to be free connected, but the circuits we're going to be interested in, the free connected ones, because we're interested for global rigidity, which requires free connectivity. Okay, so here's some notation. Given a graph, I'm going to use V sub 3 to denote the set of vertices of degree free. Okay, so we care about degree free vertices and we want to find one of them to reduce, so we're going to have this notation for the set of them all. And we're also, rather than saying vertex of degree free, I'm going to use node to refer to a vertex of degree free. And this subset, the subset V3 of nodes, will induce GV3. The subgraph induced by V3 will be called the subgraph of nodes. And so we're going to work with these objects. Okay, And it's also going to be important, and this is motivated by the second example I drew above, that H example. So a node, if you think about it instead of as a vertex of G, but think about it as a vertex in the subgraph of nodes, then G could have degree 0, 1, 2, or 3. So it's got 3 neighbors in G, but how many of those neighbors have degree 3 is the possible degrees of this node. And so we're going to split into various cases as we go. So if the degree is at most 1, then it's a leaf node. If the degree is equal to 2, it's called a series node. And if it's equal to 3, it's called a branching node. So these are their degrees in this subgraph of nodes. And the point of this is that, as we said before, I had a vertex whose neighbors were all degree 3. But forget what happens in the rest of the graph. If I try and reduce V, then I'll have to add an edge somewhere, and that will make the other vertex drop from degree 3 to degree 2. So that's always going to be bad, regardless of what happens over here. So that means we need to rule out this case. We need to find a node that's in one of the other cases, but it also means for technical reasons, what we're going to end up doing is saying, okay, there's a bad node here, and with some blocking set, and we find something else here that's a node, but if it was a series node, it might be that it has a neighbor over here. So it could be a series node in this. Maybe this is not such a useful picture, but just to complete with the sentence anyway, don't worry about it if it's not so clear. We had a bad node, which was bad because of a blocking set. And then you picked a different node elsewhere. And then over here, it might have been good, but it might have one more neighbor over here that pushes the 2 up to a 3 if you move from a subgraph of the subgraph of nodes. And so we really want to have this distinction because it will be the series ones that go up would also be bad. But I think that's probably too vague at this point. We've got a fair bit of work to do to get to that point. Yeah, so this was the illustration of part of the motivation for this separating out nodes into their degree in the subgraph of nodes into leaf, series, and branching. Okay, so another example, let's think about wheels. So wheels are a very nice class of graphs, and they're all circuits. So what is a wheel? Well, if you just keep adding degree 2s on it going round, then this is a nice minimally rigid graph in the plane, and we add one more edge, we get a nice circuit. So whatever size wheel, I mean, I could have had more vertices, if you like, just kept going, made bigger and bigger wheel around the outside. This will always be a circuit. So wheel for me, Wn, is a cycle of length n plus a cone vertex, so plus one vertex in the middle here, adjacent to everything. Okay, so what do I want to say about wheels? Well, they're special because of this subgraph of nodes thing. So in the middle, as long as the number of vertices in the wheel is at least 4 on the cycle, then the vertex in the middle will have large degree, but every other vertex will have degree 3. Okay? So if I look at the subgraph of the wheel induced by the vertices of degree 3, then I get this cycle around the outside. Okay? And notice as well, if I want to go from one wheel to another, what I would do, say, is take this edge, subdivide it, and add it to the center. So that's a nice 1 extension. And so if I wanted to undo that, I could delete this blue vertex V by deleting it and putting an edge across like that. And you can just keep going and going and going. So it's easy to see that every wheel is obtained from K4 by 1 extensions. So wheels are a nice little family of globally rigid frameworks in 2D that we can already see from the previous lecture are all done. But wheels are also exceptional in a sense that I just mentioned. So we just said that the subgraph of nodes in a wheel was a cycle. It's always a cycle around the outside of the wheel. It's everything apart from the vertex adjacent to everything else. But if you're not a wheel, then this subgraph of nodes cannot have cycles. And that's what we're going to prove next. So if the graph is not a wheel, but it is a circuit, then the subgraph of the vertices of degree 3 is acyclic. It's a forest. Okay, so let's go through that. So suppose it contains a cycle, and we're going to get a contradiction. So if this subgraph contains a cycle, we may as well choose a shortest cycle, C. So if your cycle had chords, you just pick a smaller cycle because the chord would give you a smaller cycle. So I've got some cycle with no chords, C in my subgraph of nodes. Oh, and sorry, I forgot to make a little correction here. So I want to use, but for lazy reasons, I want to use C for both the vertex set and the edge set of the cycle. So apologies for that, but you could write out V of C and E of C if you like, but I'm just going to use C for both the vertex and edge set. So G itself is not a cycle. So if I take the vertex set of G and subtract the vertices of the cycle, I still have some vertices left. Each vertex of this cycle I've found is a node because it's a part of the subgraph of nodes. And since we're not the wheel, we know there's at least two vertices outside. So in the case of the wheel, the subgraph of nodes looks like that, and there's exactly one more thing adjacent everywhere. But if I'm not the wheel, then I know there's at least two vertices outside. Okay? So now I want to count. What's the number of edges induced by the vertices outside of this particular cycle? Well, it's the number of vertices in the entire graph minus the number of edges induced by the cycle, minus the number of edges between the cycle and what's not in the cycle. So that's sort of evident. The number of edges in the whole graph stays the same. The number of edges in a cycle is the number of vertices. So that's just C. And the number of edges between the cycle and the rest of the graph is C as well. So why is that? Well, I know I have some cycle, but I also know every vertex on the cycle has degree 3. So if that's the cycle and this is the rest of the graph, there's one edge coming from there, one 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 from there. And there were no chords, so none of those ones I just drew could do something like that. So there was exactly C of those as well. But I've now got 2V minus 2C, which is the number of vertices in over here. And I've got a minus 2. But this is a proper subset of the vertex set with a minus 2 here on my count rather than at most 3. So this is a subset which contradicts the definition of a circuit. So we've proved that this subgraph of nodes, when we're not a wheel, is cycle free. Okay, is that okay?
Yeah, that's good.
Okay, so here, this is, I guess this is really completely an aside. It's not relevant to the proof I'm going through, but if you want an exercise to do, it's sort of a nice little thing to do. If you draw a planar circuit and you take a plane drawing of that circuit and you take the planar dual, then you should get another plane circuit. So that's an exercise to verify if you like. Okay, so we've started to understand a bit about this subgraph of nodes, and we want to use it to apply one reductions. So first I want to just characterize the very simple thing. So I give you a vertex of degree 3, I apply a particular one reduction. What can go wrong? I want a characterization of what can go wrong for just a one reduction at V, which adds one particular edge. I know there's 3 possible edges, which is a bit harder to understand, but just adding one of the particular choices, what can block that from working? So
Tony,
I say a one reduction at a vertex, a node, V, that adds XY among the neighbors of V is called admissible. If the graph you get, so G sub V subscript XY is saying the graph I get from G by applying a one reduction at V, adding the edge XY, that one reduction is admissible if the graph you get is a circuit. And it's non-admissible if it's not. So when is one of these one reductions admissible or non-admissible? That's this Lemma. So I take my circuit, I take a vertex of degree 3 with neighbors say X, Y, and Z. The one reduction at V adding XY is non-admissible if and only if there exists a critical set X with XY in X and V and Z not. So remember, critical set means I of X is 2X minus 3. So if there is, I mean, so I'll say the proof again in a second, but if there is such a set, then when you add x and y to it, then this goes up by 1, and so you get a subgraph that's bad because it doesn't contain these things. So one direction is kind of obvious, and the other direction isn't hard either, but let's just run through it anyway. So this is the easy direction, I say here. If such a critical set edge exists, then the edge xy adds 1 to my count for I of x, which, because v and z are not in it, in x, violates the definition of the circuit, okay? Which would tell you the one reduction is non-admissible, so that's proved one direction. Conversely, if we suppose the one reduction is non-admissible, then that means there exists some set in the smaller graph we get, which violates the circuit condition. So we know that we would have E equals 2v minus 2. That's just a very simple count. So there must be some subset which has too many edges in it, which lives in the vertex set of the smaller graph, which is actually equal to the vertex set of v minus v. Okay, so if we look in this smaller graph, then the number of edges is at most what they are in the big graph plus 1, because we only add one edge. So it follows from that x must have been critical in the big graph, because in the big graph it must satisfy the sparsity conditions, and it must fail them here. So it must go, and it can only go up by 1, so it must have been critical. And the set that violates is not a subset of G, so the critical set in G must contain x and y. So the only thing we're left to show is that Z is in it. And the point here is that we had this vertex B, and here's x and y and z. If Z is in the critical set, then you add V, and you add 1, 2, 3 edges, and you find a bad thing for your critical set, like we did in the Lemma case. So if Z is in X, then I of X plus V is I of X plus 3, but we only added one vertex, so we end up with 2x plus V minus 2, which would give us a subgraph of G, which can't happen in a circuit because, well, it just can't. So you get a contradiction, hence Z is not in X. And so that's nice, because when we want to do a one reduction, since we know that the block looks like this, it doesn't contain Z, we can also then think, well, let's look at a second one reduction, which might be blocked by YZ, but not contain X. And so you have more freedom to do things. So this is a sort of luxury, I guess, that you have in this situation that you don't always have in other problems. Okay.
Hey, Tony.
Yeah.
Can we look at the statement of this lemma?
Yeah. So I want to do a one reduction in a circuit at a particular vertex, adding a particular edge among the neighbors. And that's no good. It does not preserve the circuit property if and only if you have this property.
So Tony, when you say no good, or sometimes you say this is bad or something like that, it means that we're not preserving the circuit property.
Yeah, so I mean the one reduction is non-admissible, which means that I took a vertex in a circuit and I applied this one reduction, and what I get is not a circuit. Alex, have you seen the statement long enough now?
Yeah, thanks.
Great. Okay, so we were talking there about one reductions adding a particular edge, but as you know, there are 3 possible one reductions. You could add any of the 3 edges. So we can extend our definition of non-admissible to talk about a node being non-admissible rather than the particular one reduction. So a node V is non-admissible if none of the 3 possible one reductions gives you a circuit. Okay, and we saw earlier on with those 2 examples, G and H, that nodes may be non-admissible. So we need to understand what happens in that sort of situation. So it may be that some node is non-admissible. We need to look in the rest of the graph and use the structure that non-admissibility gives us, these critical sets, to find some vertex that is admissible. And we're going to use need to use free connectivity at some point along the way. We know that from the non-free connected counterexample. Okay, so here's a helpful lemma. So I take a circuit, and I take a subset of the vertex set, which is a critical set, such that there are at least 2 vertices in V that aren't in the critical set. So you sort of want to imagine that X is a critical set which blocks a 1 reduction at some vertex. So obviously then the V and the Z would not be in it, so you would have this at least 2 property. And the conclusion of the lemma is that outside of this circuit, there are at least 2 nodes. So if you find a node you can't reduce as a critical set, but there's at least 2 other vertices, and somewhere in that rest of the graph, there's at least 2 nodes, and you can try and do a 1 reduction there. So why is this true? Okay, so let's let X be a critical set, satisfying the hypotheses, and define Y to be the rest of the vertex set, V minus X. So X is a critical set, so it has at least 2 elements, and hence the number of edges between X and Y is at least 4. So maybe that's not quite obvious, but it's an exercise I've left here. So what's an exercise? To verify this, one way to do it is to show that every free edge separation in a circuit has the property that one side is a single vertex. So it's clearly true you can have a free edge separation because you can have vertices of degree 3, and there's a free edge separation. But if you have at least 2 vertices on the 2 sides, you can't just have free edges between them. Those sort of separations are not possible. And so you can show this by looking at the 2v minus 2 and at most 2x minus 3 edges in subgraph conditions, and just counting basically. This is an exercise to verify, but the only thing we're going to use from it is that we have at least 2 vertices in X, which we already knew, but between X and Y, there's at least 4 edges. Okay, so given that we're then just going to count, okay? So in Y, which remember Y is the vertices outside this special critical set X, we want to count the degrees of the vertices in Y. So it should be clear that what you want to do, the sum of the degrees is twice the number of edges, but we're looking at the degree in G, and we're looking at a subset of the vertex set. So it's not just twice the edges induced by Y, it's also the edges. So there's Y here and there's X here. These edges count towards the degree of vertices in Y at those ends, but they count once rather than the twice an edge within here. It counts towards the degree once here and once here. So it's twice for the edges in Y and once for the edges between X and Y. Okay, so now we just do a short sequence of equations. So the sum of the degrees of the vertices in Y, we just said that. I of Y is, well, so the dxy is just going to stay at the end all the way down for a while. So we look at 2I of Y. So this is equal to twice I of Y, and I of Y is the number of edges in the whole graph minus the number of edges induced by X minus the edges between X and Y, okay? But the edges in the whole graph are 2v minus 2, because it's a circuit. X is critical, so I of X is 2x minus 3, and the dxy stays. So now we can take 2 times 2v minus 2 minus 2x minus 3 minus d is this, if you just work it out. And then 4v minus 4x is 4y, minus 4 plus 6 is 2. These two cancel to just give a minus 1. And we said dxy was at least 4. So 2 minus at least 4 gives us at most 4y minus 2. Okay. And so now we just have the degree thing again. So the sum of the degrees of the vertices in Y is at most 4y minus 2. So even if they were, so keeping them as low as possible, they can't all be 4s. We must have something of degree less than 4 in there. So we get something of degree 3, but because this is a minus 2 rather than a minus 1, it follows there's at least 2 of them that are degree less than 4, and they're both 3s, because we can't have a degree 2. So since the degree is at least 3, each 3 gives us a minus 1 in this compared to 4s. So we get at least 2 nodes, which is what we concluded in the lemma. Okay, so we proved that one. All right. So now, if we have a non-admissible node, V, then we know it's blocked for the one reduction at x, y by a critical set x, and we can find some node outside of it. In fact, we can find two, but what we're going to do is have this picture and work on this node to find some sort of contradiction or find some sort of admissible node that we can reduce.
Tony?
Okay. Yes.
Tony? Will a series node always be admissible?
No. It won't. So I'm wondering if I can draw an example quick enough where it will work. So maybe this example I had here, this was true, wasn't it? No, they were leaf nodes because there was a free and a free. It won't be. It's not true that they're always admissible. So I bet you can make some sort of just minor edit to this kind of picture, you know, where I showed that branching nodes, if you just make one of these bigger, but still force the reduction to add this edge, then this one would stay at degree, would still degree would drop, but I can't, without taking a couple of minutes, I don't know how to make an example. So I think it's no, but and probably after the lecture, if you like, I could spend 5 minutes and come up with an example, but.
Okay, yeah, no problem. Thanks.
Yes, so I guess the answer is, unfortunately, it's not quite as simple as that. Okay, so what I want to do, we have these critical sets, but I really care about critical sets that actually block one reductions. I don't care about arbitrary critical sets. So I'm going to just refine the idea of a critical set a bit in two ways. So first of all, let's take a node with neighbor set x, y, z, node V. And if you have a critical set X, which contains two neighbors, but not the third and not the node, then the node is then the critical set is V critical for that particular node V. But it's always true that you can get sort of trivialities. So, and in fact, that the trivialities is kind of what's happening here. So it's always true that G minus V is a critical set because it's a degree-free vertex. But that's not really interesting or helpful. If you take any degree-free vertex, the entire graph minus that one vertex or the entire vertex set will give you a critical set. But what we're really going to care about is where the neighbors all have, at least one of the neighbor outside the critical set has sufficient degree. So we have this special neighbor that's not in the critical set. If that has degree-free, then non-admissibility is very definitely obvious before you worry about adding the edge xy, because if you want to add xy, then z will drop to degree 2. So they're called trivial V critical sets, and the sets we're really going to work on are node critical sets, which is a V critical set such that the degree of z is at least 4. So I want to work on critical sets which are critical for some node, i.e. they contain two of the neighbors of a node, but not the third, and the third neighbor has degree at least 4. Okay, so.
Tony, could you just draw the quick picture that goes with the V critical set? Is there some kind of schematic that?
Okay, so I have. This is my vertex V and its neighbors. So I have a critical set X is V critical if it looks like this. So it's a critical set which contains two of the neighbors and not the third. And so this set X is, as well as just being an arbitrary critical set, a set with 2x minus 3 elements, it's critical for V because it stops us doing the one reduction at V that adds the edge xy. And then it's called node critical as well, if you just say that Z is degree at least 4.
Okay, that makes sense.
Thanks.
The Z, also there's somehow a component outside, like Z isn't all by itself. Is that, how do I say this?
Yes, so it is possible that what you see in this picture here is the entire graph. So what happened in this picture, so I'll draw it a slightly different way. So we had this example a few times. So suppose this is V, and this is X, this is Y, and this is Z. Then the critical set containing X and Y is this graph. And then Z is degree free in it, and this is the trivial case. But over here, I said that Z has degree at least 4, and X is critical. So if Z had 3 neighbors over here, then that would be over full because it doesn't contain V. So one of these 3 neighbors definitely lives over here. So yeah, there is something over here as well as Z. So that's kind of one of the points of the node critical thing, because the trivial case, you can have things like this where there's nothing else. But in the node critical case, there is definitely some vertex over here in the rest of the graph.
Okay, thanks. That's perfect.
Hey, Tony.
Yeah.
I have sort of a dumb question. If I do a 1 reduction at V in this red picture, then and I add the edge in the critical set X,
yeah,
that would make the resulting graph flexible?
No, not necessarily. So for example, so what it's saying is that you have I of X is 2X minus 3, and you add 1 edge to this, so you get a subset that violates the inequality you need for circuits. It may be that you get a nice rigid graph. So for example, in the case where Z is degree free, like here, you would get K4 plus a degree 2. So it would be a perfectly valid reduction for preserving rigidity, but it would not preserve the circuit property. And that's the property we're trying to preserve at this point.
Okay, thanks.
Okay, so I'm about halfway through what I wanted to say in this lecture, but that's just good because it means I'm going slowly and hopefully people are understanding. So let's have this lemma. So we take a free connector. So this is the first point we're going to use the free connectivity condition in one of our results. A free connected circuit on at least 5 vertices. The only circuit up to 4 vertices is K4, so at least 5 vertices is not really making any assumption. Suppose that V is non-admissible and it's a leaf node. So it's a node with degree at most 1 in the subgraph of nodes. So it's got at most 1 neighbor, which is also degree free. Then there exists 2 V critical sets X and Y, which intersect in at least 2 vertices, and their union is the entire graph, except for the vertex V that we're talking about. So that's the first part of the lemma. And then there's a moreover, if the vertex V is adjacent to a node Z, so V is a non-admissible leaf node, so if it's adjacent to a node Z, that's the degree exactly 1 case, then these 2 critical sets, the V critical sets X and Y, you can choose them to satisfy Z as in the intersection. So we have this reduction, and let's say Z is this one, and X and Y are here. If it's true that V is adjacent to Z and Z is a node, then as well as just existing 2 V critical sets, which you'd have the 3 possibilities for like that, it's true that we can choose the X and Y to be the 2 that intersect in Z. Okay, so that's the lemma. I think given that it's 10 to, I'll prove the lemma and then stop for questions, and we'll just continue next time from that point. Okay, so let's say neighbors of V are X, Y, Z as usual. So what we're doing, we have a non-admissible leaf node, and we're trying to show that there are 2 critical sets X and Y with these 2 properties, that they intersect in at least 2 points, and their union is V minus V. So our vertex is non-admissible, so we're blocked from adding XY, we're blocked from adding XZ, and we're blocked from adding YZ. So that tells us there are 3 V critical sets. Let's say X contains Y and Z, but not V and X. Y contains X and Z, not V and Y. Z contains X and Y, not V and Z. So I have these 3 blocking sets, X, Y, and Z, and I'm going to show that the union of some pair of them is the X and Y I want in the lemma. So if any 2 of them intersect in at least 2 vertices, their union will be critical, And then when I add V, I'll get everything, right? So suppose I have this set and this set, this is V. If this is X and Y and there's at least 2 vertices in here, then X union Y will be critical. So X union Y union V will be equal to 2X union Y union V minus 2. And hence it must be the entire circuit. So that would be the intersection at least 2 I wanted. And I'd have that X union Y equal V minus V. So I'm going to suppose it doesn't happen. If I get the intersection, I get that I've got everything. So suppose no 2 of these sets intersect in at least 2 vertices, okay? So just to do the picture, maybe do the picture this way, what that says is I've got this graph where I've got my X, my Y, and my Z, and the 3 critical sets are the 3 blobs, and it's exactly like that. Okay, so I want to just do some counting. So just relatively quickly, let M denote the number of edges induced by the union of these 3 critical sets. So I think I had it as X, Z, and Y like that in the picture. Okay, so the number of edges in the union, it's a subset which doesn't include the vertex V, so it's at most twice the union minus 3, but it's equal to the number of edges in X plus the edges in Y plus the edges in Z plus the ones in the union which don't belong to the 3 parts which we defined as N. X is critical, so you get this. Y is critical, so you get this. And Z is critical, so you get that. They intersect. Well, let's just put it together. X, Y, and Z, put them all together. There was 3 minus 3, so 2 times minus 3 minus 1 minus 3, so that's still fine. And then there were exactly these 3 vertices, X, Y, and Z in common, so I get to this. But now I have that this is greater than or equal to this, so it must actually be that greater than or equal to is an equality, and the M is 0. Okay, but now I also have the number of edges from the vertex V to X union Y union Z is 3. That's sort of evident. X union Y union Z includes X, Y, and Z, so you get all 3 of the edges. So when I add them in, I get the entire graph, as I was just saying before, in the same way. So if I add them in, I get a circuit. I get a subset with 2x minus 2, and so it must be the entire thing, and hence X union Y union Z is V minus V. So I wanted a pair of these things to be all of V minus V. So far I've shown that all 3 of them are in this case where there's only single vertices in the intersections. So now I want to use the free connectivity hypothesis to get a contradiction. So I know I have at least 5 vertices. So if you count up, there's X, there's Y, there's Z, there's V, that's 4. So there's at least 1 more vertex somewhere. So I can assume that one of these 3 blobs has a vertex in it. Say it's X, then I've got in X, I've got Y and Z and that vertex, so it has at least 3 elements, okay? But we know there were no edges induced by the union of X, Y, and Z that weren't in the individual blobs. So what that says is that this pair of vertices, Y and Z, separates this vertex in X from anything over here or over here. In fact, YZ is a 2-vertex separation in the graph, which separates this vertex from the rest. So you contradict the hypothesis that you're free connected. Okay, so that was what happened if all 3 of the intersections of these 3 critical sets had size 1. So for some pair, and I've just called it X and Y because I can just relabel if I like, you do have at least 2 things in the intersection, and hence the union is critical. And as we said before, that means that you add V and its 3 edges back, you must get the entire thing. So that's the first part of the lemma. The second part, the moreover, was that we could assume that if Z is a node, we could put Z in the intersection of X and Y. And I know in my X and Y, Z is actually there, but I could have relabeled to make this assumption. So I need to check that's actually true. Okay, so suppose Z is a node. So here's a special case. If x, z, and y, z are both edges, then the picture looks like this. My two blobs, the blob that was including x and z is just this single edge, and the blob that was y and z is just this single edge. But now z is a node, so very definitely x, y separates z from the vertices over here. Okay? We know the number of vertices was not 4, it was at least 5, so there was something over here, otherwise I'd have had this edge and been K4. Okay, so again, that would have been a contradiction of free connectivity. So I can assume one of these edges doesn't exist. Let's say it's the edge from y to z. So we know that this edge doesn't exist. Now we know that this is blocked by a critical set x, and it has at least 3 elements, so x is at least 3. If you have a critical set and at least 3 elements, it's a Lemma graph, it's a 2-3 type graph you get, so it's 2 connected. Hence, the vertex z here has at least 2 neighbors in the subgraph x, in the vertex set of x. If z has no neighbors in y, so remember y could just be this edge or it could be a bigger blob. So if z has no neighbors in y, then it would be true that this edge x, z is not present, otherwise that would contradict having no neighbors. So that means that there's at least a vertex here, but it would also say that z has no neighbors in this bit, so z is an isolated vertex in the subgraph gy, but we just said the subgraph gy is 2 connected, so it can't have an isolated vertex, so that's a contradiction. Hence, z has a neighbor over here, but z has degree 3, and you can see I've got 1, 2, 3, plus the edge to v, 4. So one of these 2 vertices must actually be in this intersection with z. And so x intersect y is at least 2. There's a second thing in there. And now again, x union y is critical, and x union y equals v minus v, as we did before. Okay, so I should stop there. I was going to next get to the really key technical bit, but we'll delay that until next time, because I've already run quite far over. Let me just slide this right to the end, because I just wanted to remind people that the next lecture is not for a while. So I'm happy to hang around for questions, but just to remind you first, the next lecture is actually on the 5th of March, because next week we have the rigidity workshop, and then the Monday to Wednesday of the following week, we have the materials mini symposium. So I think it's 2 weeks today, Friday the 5th of March, is the next lecture we'll have in this course. So thank you for bearing with me through some technical combinatorics.